Welcome to Systemic Stack. My name is Kabir Anand. This is episode 20 of the System Engineering series, and today we will explore Saga Pattern, distributed transactions, in a way that helps you prepare for system engineering interviews on this topic. When microservices break traditional ACD boundaries, you've got to manage consistency yourself. We'll look at the two main flavors, orchestration and choreography, to see how they handle complex failures. Mastering these patterns is how you show interviewers you can actually build reliable long-running workflows in a distributed environment. It starts by tackling the distributed workflow dilemma, where business processes crossing service boundaries break traditional AC transactions. We'll define distributed transaction management and introduce the Saga concept as a sequence of local transactions. You're going to learn about the two major architectural styles, orchestration, which uses a central brain to coordinate steps, and choreography, which relies on a decentralized event-driven flow. Well, since things often go wrong in distributed systems, we'll also examine the outbox pattern for event persistence and the logic of compensation, the specific way we undo actions without a physical rollback. We'll contrast forward and backward recovery models before putting these ideas into practice with real-world scenarios like order management, payments, and complex travel bookings. Finally, we'll dive into some heavy-hitting interview insights, looking at the trade-offs between visibility and decoupling when choosing between 2PC and Sagas. By the end, you'll understand exactly how to design resilient workflows that maintain data consistency at scale. Let's set the scene with a real engineering situation you'll probably find yourself in during a system design interview. Imagine you're building a global e-commerce platform that needs to handle thousands of orders per second. Each order touches three distinct services: order management, payment processing, and inventory. In the old days, you'd just wrap all those database updates in one big transaction and call it a day. But at this scale, each of those services has its own database, maybe even using different technologies. If the payment service succeeds, but the inventory service fails because an item just went out of stock, you can't just roll back a database call that happened 3 services ago. This is where the risk of data inconsistency becomes a real threat to the business. Without a pattern like Saga, you'd end up with customers who've paid for items that don't exist, leading to a massive loss of trust and operational chaos. Understanding this scenario is how you prove you're thinking about production-grade reliability. Now, let's get into the mechanics of the Saga pattern itself. It works by treating a complex business process as a series of small local transactions. Each service involved performs its own update and then emits an event or message to trigger the next step in the chain. This approach is essential because it respects the autonomy of microservices, ensuring that one service's database doesn't need to know the internal details of another. Why is this so popular in high-end systems? It's because it avoids the long-lived locks that destroy performance in distributed environments. However, you have to watch out for the main failure mode here. Atomicity is lost at the global level. Unlike a single database transaction, there's no magic button to undo everything instantly if step 4 fails. You are essentially trading off the simplicity of ACID for the scalability of base consistency. In an interview, being able to articulate that you're knowingly making this trade-off for performance is a huge green flag for senior roles. The core of our problem is what we call the distributed workflow dilemma. When you have a process spanning 3 separate services like order, payment, and stock, each one has its own isolated database. This isolation is great for scaling, but it creates a massive headache for consistency. You can't use a standard SQL begin transaction across 3 different network-connected databases. If the network blips or a service crashes midway, you are left in a state where the data is no longer synchronized. What matters here is that a business can't survive with ghost orders that were paid for but never reserved in inventory. The typical failure mode in native implementations is the dual write problem, where you update a database but fail to notify the next service. Without a formal pattern like Saga, you'll inevitably face race conditions and data corruption that are nearly impossible to debug after the fact. It's these kinds of boundary issues that interviewers use to see if you actually understand the limits of distributed computing. Defining distributed transaction management starts with acknowledging that we are moving away from the safety net of the two-phase commit protocol, or 2PC. While 2PC works by having a coordinator ask every participant to prepare and then commit in unison, it's notoriously slow and creates a single point of failure. In a modern microservices setup, we need a way to manage data consistency without those heavy blocking locks. Distributed transaction management in Sagas is all about coordinating these independent local transactions so that they eventually reach a consistent state. What matters here is that it allows each service to remain highly available and performant. The failure mode you have to worry about here is lack of isolation. Since other transactions can see the intermediate changes before the entire saga is complete, you can run into dirty reads or lost updates. In an interview, you should be ready to explain how you'd mitigate these isolation issues, perhaps by using a pending state or versioning, to show you've thought through the deep consistency challenges. The Saga concept relies on breaking a workflow into local sequences. Each step in the sequence is a standard local transaction that updates a database and then publishes a message to the next service. It's like a relay race where each runner does their part and then passes the baton. This design is crucial because it keeps each step short-lived, which reduces database contention and improves overall system throughput. However, the complexity lies in what happens when the baton gets dropped. A major failure mode is message loss or duplicate processing. If a message is lost, the whole saga stalls forever. If it's duplicated, you might bill a customer twice. This is why you need to ensure your message broker is reliable and your services are idempotent. When an interviewer asks how you'd handle a partial success in a distributed system, this concept of sequential local updates is your foundational answer. It shows you know how to build a chain of events that is both decoupled and progress-oriented. Let's talk about Saga Orchestration, which is essentially the central brain approach. In this model, you have one dedicated service, the orchestrator, that tells every other participant exactly what to do and when to do it. It's like a conductor leading an orchestra. What matters here is that it provides a single point of truth for the entire workflow state, making it much easier to monitor and debug when things go sideways. You can look in one place to see exactly where an order is stuck. However, there are two main risks. The orchestrator can become a single point of failure, and it can also become a bottleneck if it's managing too much logic. If the orchestrator goes down, the entire business process grinds to a halt. In an interview, use this as a chance to talk about trade-offs. Orchestration is fantastic for complex workflows where you need high visibility, but you have to be careful not to turn it into a god service that knows too much about everyone else's business. On the flip side, we have Saga Choreography, which is a decentralized, event-driven flow. In this setup, there is no central brain. Instead, each service knows which events to listen for and what to do next. It's like a dance where every performer knows their cues without a director shouting orders. What matters here is that it maximizes decoupling. Services don't even need to know the others exist. It's incredibly flexible and scales beautifully. But here's the catch. The failure mode here is a complete loss of visibility. When you have 20 services exchanging events, it becomes very difficult to figure out why a specific transaction failed or where it currently is in the system. You also risk creating cyclical dependencies, where service A triggers B, which triggers C, which accidentally triggers A again. In an interview, you'd choose choreography for simpler, highly scalable workflows, but you'd better have a plan for distributed tracing and monitoring to explain how you'll actually keep track of what's happening in production. To make choreography actually work in the real world, you have to solve the problem of event persistence. You can't just update your database and then send a message to a broker in two separate steps, because one might succeed while the other fails. This is the classic dual write failure mode. The outbox pattern is our savior here. It works by saving the event into an outbox table within the same local transaction as your business data. A separate process then polls that table and pushes the messages to the broker. What matters here is that it guarantees that your database update and your event notification are atomic. It's all or nothing. If you don't use this, your system will eventually drift out of sync and you will spend your weekends manually fixing data. Interviewers love to dig into this specific detail because it separates people who just know the theory from those who've actually built reliable distributed systems. It's the difference between a system that looks good on paper and one that survives a network partition. Since we can't do a physical rollback in a distributed system, we have to master the art of compensation. A compensating transaction is a semantic undo. For example, if you've already authorized a payment but the shipping service fails, you can't just delete the payment record. You have to issue a refund. What matters here is that it brings the system back to a consistent business state, even if the technical state has moved forward. You need to design these undo actions for every single step of your saga. The failure mode to watch for is a nested failure, where the compensation itself fails. If your refund service is down while you're trying to undo an order, you're in a very awkward position. In a system design interview, always mention that compensating transactions must be idempotent because they might be retried multiple times. Showing that you understand the difference between a technical rollback and a business level compensation shows a high level of senior level maturity and practical experience with long-running workflows. When things go wrong, you have to choose between two main recovery strategies, forward and backward recovery. Forward recovery is about pushing through. If a step fails, you keep retrying it until it succeeds, which works best when failures are transient, like a temporary network blip. Backward recovery is the undo path, where you execute all the compensating transactions for the steps that already finished. What matters here is that not every error can be fixed with a retry. If a customer has no money, no amount of retrying will make that payment succeed. The failure mode for forward recovery is getting stuck in an infinite retry loop that consumes resources. For backward recovery, it's the risk of failing to undo a high-stakes action. In an interview, the key is to explain that you'd use forward recovery for critical steps that must happen and backward recovery for business logic errors. Being able to distinguish when to use each strategy demonstrates that you're thinking about the specific nature of the failure rather than just applying a one-size-fits-all solution. Let's look at a concrete use case. Order management. When a user clicks buy, we might authorize their card and then check the inventory. If we find out the item is actually out of stock after the payment is already authorized, we have to trigger a compensation flow to cancel that authorization. What matters here is that it prevents the customer from being charged for something they'll never receive. In this scenario, the failure mode is often a race condition where the stock level changes between the time the user added it to the cart and the time the payment went through. Without a solid Saga implementation, you'd end up with a manual reconciliation nightmare for your support team. In an interview, walk through this flow step by step. First the happy path, then the specific error point, and finally how the system recovers. It's a classic example that everyone understands, making it perfect for demonstrating your grasp of the Saga pattern's practical utility and its necessity in high-volume e-commerce environments. Payment processing is another great use case for Sagas, especially when dealing with multi-step wallet deductions and external gateways. Imagine a scenario where you have to deduct money from a user's internal credit balance and then call an external API like Stripe for the remainder. These two systems fail in completely different ways. If the external gateway call fails after the internal balance is deducted, you need a way to reliably credit that money back. What matters here is that financial data demands 100% accuracy. You can't just lose money in the system. The common failure mode here is a timeout on the external API where you don't know if the payment actually went through or not. This is why you need a Saga to manage that uncertainty. In an interview, focus on how you'd use a pending state and an orchestrator to manage these multi-leg financial transactions. It shows you're capable of handling high-stakes data where consistency is non-negotiable and failure handling must be bulletproof. Travel reservations offer perhaps the most complex sequential dependencies. Think about booking a flight, a hotel, and a car rental all at once. If you successfully book the flight, but the hotel is suddenly unavailable, you can't just leave the user with a flight to nowhere. You have to call the airline's API to cancel that flight. What matters here is that travel APIs are often slow and have very specific rules for cancellations and refunds. A major failure mode here is partial availability, where the car and flight are booked, but the hotel is gone and the user's credit card has already been hit. Sagas manage this by ensuring that the car and flight are only finalized once every part of the trip is secured. In an interview, highlight how you would handle these long-running processes that might take seconds or even minutes to complete. It's the perfect use case for showing how Sagas manage external world side effects that are outside of your direct database control. When you are in an interview, you should expect two primary comparisons, 2PC versus Sagas and orchestration versus choreography. You need to be ready to explain that while 2PC offers strong consistency, it's a performance killer in high latency distributed environments because it locks resources. Sagas, on the other hand, trade off that immediate consistency for high availability and throughput. A common failure mode in these interviews is failing to address observability. If you suggest a choreography-based Saga, you must mention how you will track the state of a transaction that spans 5 different services. You need distributed tracing or a centralized log. If you don't, the interviewer will think you've never actually run this in production. You should also justify why orchestration is often better for complex business logic as it puts the brain in one place, whereas choreography is great for simple, highly decoupled systems. Being able to weigh these trade-offs is what gives off that senior signal that companies are looking for. You are now equipped with the architectural tools to design resilient, consistent workflows in distributed environments. We've covered a lot of ground, from the basic dilemma of distributed databases to the complex trade-offs between central orchestration and event-driven choreography. Remember, the Saga pattern is not a one-size-fits-all solution. It's a strategy for managing complexity at scale. The key is to always think about your failure modes first. How will you undo an action, and how will you know if a process is stuck? What matters here is that as systems grow, the number of things that can go wrong grows exponentially. If you can build systems that fail gracefully and maintain data integrity, you're already ahead of most developers. In your next project or interview, don't just reach for the simplest solution. Think about the consistency requirements and choose the right pattern for the job. Mastering these distributed patterns is exactly how you level up from a coder to a system architect. So we've broken down how to maintain consistency when your business logic outgrows a single database. The Saga pattern is our go-to solution for distributed transactions, replacing rigid ACID locks with a sequence of independent local updates. We explore the two main implementation styles: choreography, where services react to events, and orchestration, which uses a central brain to manage the flow. In a system design interview, your ability to choose between these is a huge signal. You've got to justify why you'd pick the decoupled nature of choreography versus the simplified visibility of an orchestrator. Remember, because we can't physically roll back a remote database, we rely on compensating transactions to undo work semantically, like issuing a refund rather than just deleting a record. Well, mastering these failure modes and ensuring event atomicity with the outbox pattern is exactly what makes your distributed workflows actually production ready. You're now equipped to handle complex sequences across any number of microservices. Well, that wraps up our deep dive into the Saga pattern. When you're tackling this in a system design interview, remember that your choice between orchestration and choreography usually comes down to the trade-off between central visibility and service decoupling. We looked at three main use cases: orders, payments, and travel, to show how those local transactions and compensations actually keep things consistent without a global log. If you want more, make sure to subscribe and check the description for the full course details. In the next episode, we will discuss idempotent APIs, where we'll discuss situation, core understanding, definition. Catch you later and good luck with your designs.